Okay, so welcome back to this next video in which we are discussing Cys-Loop receptors, or Cys-Loop ligand-gated ion channels if you prefer. Okay, so in the previous video what we discussed was the transmembrane domain of Cys-Loop ligand-gated ion channels, and we discussed importantly that the M2 helices of each of the Cys-Loop ligand-gated ion channel subunits is what lines the pore of the Cys-Loop ligand-gated ion channel. Okay, and we discussed that the way that you close the pore is that you have this hydrophobic girdle which involves hydrophobic residues in the 5 M2 helices, all interacting with one another and holding the M2 helices inwards at this central point here, which narrows the pore basically. So to open the pore, what you then need to do is just break apart these interactions between these hydrophobic residues, which are valine and leucine residues, and then the M2 helices can fall back outwards, basically recoiling back outwards, opening the pore for ions to move through it. Okay, right. So now what I want to turn my attention to is the intracellular domain, okay, which is a domain that is only, remember, present on the mammalian Cys-Loop ligand-gated ion channels, so the nicotinic acetylcholine receptors, the GABA A receptors, the glycine receptors, the 5-HT3 receptors, okay? And then once we've done that, we will move on to the extracellular domain, which is present for all of the examples of Cys-Loop ligand-gated ion channels that we've discussed. Okay, right. So firstly, let's then discuss this intracellular domain. So this intracellular domain is made from the intracellular loops of the subunits of the Cys-Loop ligand-gated ion channel. Okay, so firstly, let me just remind you of where the intracellular loop for each Cys-Loop ligand-gated ion channel subunit is. Okay, so I'll just draw out this picture of a Cys-Loop ligand-gated ion channel subunit once again. Okay, so here is the intracellular loop here between the 3rd and 4th membrane-spanning alpha helices. So there's the N and C terminus for our Cys-Loop ligand-gated ion channel subunit. Here's the Cys-Loop, and I'll just colour a few bits in here. Here are our 4 membrane-spanning alpha helices, and this is the portion that we're now interested in, this intracellular loop between M3 and M4 helices, which is much bigger than the intracellular loop that you've got in between M1 and M2. That one's a tiny little loop. This is much bigger, and this is called the intracellular loop, okay, also called the M3-M4 loop. Okay, right. And this portion is the portion that is actually going to make the intracellular domains of mammalian Cys-Loop ligand-gated ion channels. So it's not going to be present on the Cys-Loop ligand-gated ion channel subunits of the prokaryotic Cys-Loop ligand-gated ion channels, ELIC and GLIC. Neither is it going to be present on the glucial Cys-Loop ligand-gated ion channel in the worms. Okay, and therefore they're not going to have intracellular domains. So let me show you now how this works. So I'll start now by drawing out the transmembrane domain of my Cys-Loop ligand-gated ion channel, and now we're going to add on the intracellular domain onto that transmembrane domain. We're still going to be without the extracellular domain, so I'm not adding the extracellular domain on yet, okay, because we haven't studied that yet. So here is the plasma membrane here. Here is our transmembrane domain, which we have now heavily studied, okay, made up out of the 5 separate subunit transmembrane domain portions, okay, and now basically dangling down from each one of these 5 subunits transmembrane domain, you're now going to have one of these intracellular loops. So I'll put this here. So here is the intracellular loop dangling down from this subunit here, and I'll colour it in turquoise again. So here is this intracellular loop here, okay. Then that middle subunit there will also have one dangling down between M3 and M4, and remember M3 is positioned here and M4 is positioned kind of here, okay. So that's why I'm drawing these to this sort of the side of the receptor subunit. Okay, here I'll colour this intracellular loop also in turquoise, and then I might even show the one over here. Okay, there is that final one that we have visible to us looking from this angle's intracellular loop. Okay, but every single one of the cis-loop nicotinic ion channel subunits will have one of these intracellular loops, providing, of course, it's a mammalian cis-loop nicotinic ion channel. Okay, and they are going to form the intracellular domain. So what do these actually do? Well, basically, we think they all end up binding together. We think this portion here comes into the center with this portion here and this portion here, and they end up binding together. So now let me show you another picture. Let me show you this picture looking from below, basically, and I'll show you what we think is going to happen. Okay, so here is the transmembrane domain from below here. Okay, there's the pore here. Okay, now I'll split it up into the separate subunits. So here is one subunit, here is another, third one, and a fourth one. Okay, right, now I'm going to show the intracellular loops coming down from here. Okay, and basically we think they all come together in the center. So here's one intracellular loop, here's the intracellular loop of this subunit, and I'm going to have to colour it in so that they actually show up. So here is one intracellular loop, here's the intracellular loop of this subunit here. Okay, again, here is the intracellular loop of this subunit here. Okay, now just put on the other ones before I colour them in. Then this one here, and this one here, and we think they all come together like this. And it's often compared to a hanging basket in its arrangement, basically. Okay, like so. And what we think, then, is that ions that want to move through the channel, they have to go through these gaps between these intracellular loops. So here's a gap, here's a gap, here's a gap, and here's another gap, and then there's the final gap. So we think the ions move through these gaps between the intracellular loops to gain access to the pore that's underneath there. Okay, so this is often compared, as I say, to a hanging basket sort of a structure here. Okay, so what does this intracellular domain then actually do? That's its structure. Okay, what is it believed to actually do? Well, it's not really known that well what it actually does yet. It's still an area of active research. And one of the reasons that we don't really know what it does is because ELIC, GLIC, and GluCl, which are so heavily studied, okay, because we have X-ray crystal structures of those, don't have this domain, and therefore, you know, these huge areas which have been studied very intently don't have this portion, okay, and therefore haven't provided any information on this portion, whereas they have provided information on other portions. Okay, so that's one of the reasons it's not very well understood. But what we think it's involved in doing is targeting the cis-loop ligand-gated ion channels in mammals to the portions of membrane where they're needed, so often postsynaptic membranes, basically. So we think it's involved in targeting these cis-loop ligand-gated ion channels to portions of membrane which are actually involved in synapses, okay, so that they don't just end up in random portions of the membrane, basically. Okay, so that's the function that we think is really important for the intracellular domain, targeting, basically, the cis-loop ligand-gated ion channel to the right location. Okay, so this is the intracellular domain then, and that's all I'm really going to say about the intracellular domain. Okay, now what we're going to move on to is a domain that all of the different cis-loop ligand-gated ion channels, prokaryotic, worms, mammalian, they all have this next domain. Okay, and this is a really important domain now. So we're going to move on to the extracellular domain. Okay, this domain in blue, which we haven't previously looked at that much at all. All we've seen previously is that it consists of a cis-loop, or rather it has a cis-loop in it. But what we're about to see is that it contains a lot more than just the cis-loop. So that's my first message, really. It contains a lot more than just the cis-loop. Okay, right. So it's actually going to contain a structure known as a beta sandwich. So first let me just put the title here. So we're now going to study the extracellular domain. Okay, right. So if I just bring back that picture of the entire cis-loop ligand-gated ion channel just to get an important message across. Basically, the extracellular domain here that I'm outlining now, this is the extracellular domain corresponding to the same subunit as this transmembrane domain and this intracellular loop here. So what I'm trying to say is that the subunits of the cis-loop ligangated ion channels, their different portions are arranged in the full pentamer in the obvious way that you would expect. It's not the case that this bit over here corresponds to this transmembrane domain, which corresponds to this intracellular domain. Okay, no, it's far simpler than that. Everything's sat on top of one another, basically. So the extracellular domain of one subunit sits on top of the transmembrane domain of that subunit, which sits on top of the intracellular domain of that subunit, basically. Okay, so that's one important message. Okay, the next important message is what the concept of a beta sandwich is. Okay, so these extracellular domains are going to contain beta sandwich structures, and I'm going to actually show you the structure of the beta sandwich of the extracellular domain in a moment, but firstly let me just explain the basic concept of a beta sandwich. So basically the idea is that you create two beta sheets, okay, and stack those two beta sheets on top of one another. So if I show this, or rather parallel to one another, in the case of these receptors in this case. Okay, so there's one beta sheet represented there, and there's another beta sheet. So remember, beta sheets are made up by parallel and anti-parallel beta strands which interact through hydrogen bonds which form through the core peptide links of the polypeptide rather than the R groups, and are therefore a secondary structure. Okay, to make a beta sandwich, all you do is create two beta sheets and stack them on one another, basically like so. Okay, that's the basic concept of what a beta sandwich is, and the extracellular domain of our cis-loop ligangated ion channel subunits is going to contain one of these beta sandwiches. Okay, so the next thing that I want to talk about is how people talk about the poles of the extracellular domains, basically. There is a positive side and there is a negative side, and I want to tell you which side is the positive side and which side is the negative side. So basically, we're going to draw this picture here out again, but we're going to draw it viewed from the top. Okay, so now I'm going to look down on the top of the extracellular domains of my 5 cis-loop ligangated ion channel subunits, basically. Okay, so what I'm now going to see then is a picture that looks like this. Okay, so here is the beginning of the pore here. Well, it's the hole, the central cavity that will lead to the pore. The pore, strictly speaking, is the bit through the transmembrane domain. Okay, but you have an equivalent cavity that's continuous with the pore of the transmembrane domain that goes through the extracellular domain here. Okay, and here are 5 separate subunits of the cis-loop ligangated ion channel's extracellular domains, and we're viewing this from the extracellular side. Okay, so not from the transmembrane domain's point of view, from above, basically. Okay, now, basically this side of each of these extracellular domains is considered the positive side, and this side the negative side. Okay, and the positive side will correspond to one of these beta sheets. Okay, and the negative side will correspond to the other beta sheet. Okay, so the positive side corresponds to what's known as the outer sheet of the beta sandwich. Okay, and so I'll just put a positive there. Okay, and then the negative side corresponds to an inner sheet of the beta sandwich. Okay, so basically in this structure here, you're going to have one beta sheet on this side and the other beta sheet of the sandwich on the other side. Okay, so effectively we are seeing this from this aspect. Okay, when you look down like this, you will be looking down on this structure from this sort of aspect, and this is the peripheral portion, and this is the portion that faces the pore. Okay, that will become more apparent in a moment. Okay, so every single one of the extracellular domains of these cis-loop ligangated ion channel subunits is going to have this same polarity. Here's a positive side, here's a negative side, here's a positive side, here's a negative side. So negative side will always be clockwise of the positive side, basically. here's the positive side, here's the negative side, here's the positive side, here's the negative side. And as I say, the positive side corresponds to one of these beta sheets, and the negative side corresponds to the other beta sheet. Okay, so if I now draw another picture of this, I'm going to chop out just one of these subunits here. Okay, and we're looking at its extracellular domain from above. Okay, basically the positive side will have the outer sheet viewed from above here. Okay, like so. And then the negative side will have the inner sheet, again viewed from above, and these form that beta sandwich basically. So we are now only seeing the tops of these sheets, this bit here and this bit here. So this bit is this bit is this bit. So the positive side of the extracellular domain of each subunit corresponds to this outer beta sheet of the beta sandwich, and the negative side of each extracellular domain of each subunit corresponds to the inner sheet of this beta sandwich. Okay, so each of these sheets will have a portion that faces into the pore or the cavity here, the central cavity, and a portion that faces out to the periphery. Okay, so now what we are going to do is we are going to study the actual way in which the polypeptide forms these two beta sheets in cis-loop thick-and-gated ion channels. And we're going to do this because we want to understand what loop A, B, C, D, E, and F are, which everyone always talks about in the literature on cis-loop thick-and-gated ion channels with regards to the binding sites. But really, to understand them properly, you do need to understand the structure of the transmembrane domain. Okay, sorry, the extracellular domain, not the transmembrane domain. Okay, so we're going to look at how the polypeptide forms these two beta sheets and forms, therefore, this beta sandwich extracellular domain here. Okay, when doing this, we will see the cis-loop structure, okay, which is one of the loops that connects the two beta sheets together. Okay, right, so I'm now going to colour in these different sheets in different colours. Okay, so the outer sheet I'm going to represent in red, and the inner sheet I'm going to keep being represented in blue. Okay, and the way I'm going to draw this is I'm going to draw it looking from this aspect here. Okay, so we're now going to go down there and look from that side where we are seeing the positive sheet at the front and then the negative sheet at the back, or the outer sheet at the front and the negative or inner sheet at the back. Okay, so let me now then draw this. Okay, so here is going to be this positive sheet right at the front here. Okay, which is the one that when we view from that angle we're going to see first. Okay, so we're going to represent the beta strands of this sheet in red, okay, and then behind it, and I'm going to draw them separately out simply because if I try and actually show this behind this, it will just be a nightmare to actually make sense of. So I'm going to separate them out so that we can actually make sense of this picture. Okay, but in reality this sheet should be sitting directly behind the outer sheet here. Okay, this is going to represent the inner sheet, which we're going to colour the beta strands of in blue. Okay. Right, so I'll say again, this sheet should be behind this sheet, and we are viewing from this side, so we are seeing the outer sheet in front and the inner sheet behind. This is the outer sheet, this is the inner sheet. Okay, right, so where is the N-terminus then of the polypeptide? Well, the N-terminus will start up here. Okay, this is the N-terminus of our cis-loop ligand-gated ion channel subunit. Okay, now what's going to happen is it's going to form the first beta strand of this inner sheet here. Okay, so let me just colour this in. So as I say, I'm going to colour in the beta strands of the inner sheet in blue, whilst I'm going to colour the beta strands of the outer sheet here in red. Okay, so that first beta strand of this inner sheet here, or the negative sheet if you like, this bit here, or this bit, is going to be called beta 1. Oh, and I should also say, this side is the side that faces into the pore, okay, like on this picture here. So this side and this side will be facing into the pore. This side and this side will be facing out to the peripheral world, basically, to the membrane, or, so yeah. So that will be facing out away from the cavity. Okay, so here is the first beta strands then of this inner sheet. Okay, then what's going to happen is the polypeptide is going to have a little loop here, and then it's going to go back up, and it will form an anti-parallel beta strand with that first beta strand, and this second beta strand is called the beta 2 strand. Okay, so I'll colour this strand in as well in blue, and I'll put arrows to show which direction it's going. So that's an anti-parallel beta strand beta 1, but it can still form nice interactions with beta 1. Now, in addition, I want to colour in this loop here because this is going to be really important later when we want to come on to the gating mechanism. Okay, this is dangling down at the bottom. This is the top of our extracellular domain here. This is the bottom, so this is going to be going towards the transmembrane domain, which will be below here. And in fact, this loop is going to make contact with the M2 helix, and it's how changes in this extracellular domain are going to be transmitted down to changes in the M2 helix to try and disturb the hydrophobic girdle and open up the pore, basically. Okay, and this special loop that we have between beta 1 and beta 2 is quite simply called the beta 1, beta 2 loop. Okay, right. Then after the beta 2 strand, what's going to happen is the polypeptide is going to move inwards a little bit, and we're going to form a little beta strand here, which will be beta 3. Now this isn't as big as beta 1 and beta 2, so it's not going to go quite all the way down the length that beta 1 and beta 2 go down. Okay, but it is still going to contribute to this beta sheet, and I should stress that we're going to fill in this gap here. There's going to be other beta strands in here. Okay, so it will form a complete sheet once we're finished. Okay, then after beta 3, we're finally going to now move over to this outer or positive sheet over here. Okay, with our first beta strand in the positive sheet. So let me show this. So here it comes. Here's the polypeptide now moving from the outer sheet to the inner sheet. And I'll stress again that although this looks like a massive gap that it's just crossed, in reality these two will be much closer, and therefore it will be a much smaller gap to bridge. Okay, then what you're going to have is a beta strand going down like so. Okay, and this beta strand I will colour in red because it's in the outer sheet. Okay, and it now is called beta 4. Okay, so we're just numbering them in the order that they occur in the polypeptide, basically. Okay, so here is beta 4. Okay, now the next thing then that I want to show is it now goes back to the inner sheet here. Okay, so it's going to move back to the negative sheet. Okay, like so. So now the polypeptide is going to loop back, and again, although this looks like a massive journey, in reality they've been much closer than the way I've drawn them. I've drawn them so far apart so that it's easy to understand. Okay, so here now is another beta sheet in the inner sheet. Oh, sorry, another beta strand in the inner sheet here. Okay, and that beta strand is called beta 5. Okay, now there's another important bit that I want to stress here, which is this portion of this loop here that's near the outer sheet here, okay, which I'm going to colour in orange. Now, this is one of these loops that I said was the basis for why we want to look at this in so much detail anyway, so that we understand what these loops truly are. This is what's known as a loop A. Okay, now I'm going to let the cat out of the bag here. Basically, the binding sites for ligand molecules in cis-loop ligand-gated ion channels are in between two receptor subunits. Okay, they're at the interface between two cis-loop ligand-gated ion channel subunits. Okay, so basically, the binding site, let's say, between these two here, is going to involve portions from the positive aspect of this extracellular domain and from the negative aspect of this extracellular domain. Okay, so which portions are actually going to be involved? Well, these are these special loops, and loop A is one of these special loops that's actually going to be involved in forming the binding site on the positive side of a extracellular domain of a cis-loop ligand-gated ion channel subunit. Okay, so this will be on this positive side here and will be contributing to any binding site in between these two here. So that's one of these really important loops. So that's a loop A in between beta 4 and beta 5 over there. And again, I'll stress that This looks like a massive journey, but it's a small journey in reality. But it's the portion that's near the outer sheet here, and therefore on the positive face of our extracellular domain, that's actually going to be contributing to the binding site. Okay, right. Then what's going to happen is beta 4 will loop back around, and then you'll have beta 5 will loop back around, and you'll then have beta 6 here. So here's our 6th beta strand, and now we're forming a nice beta sheet there. Okay, so here is another beta strand in this inner sheet over here. Okay, now there's another one of these important loops that contributes to the binding site that I haven't highlighted yet, but I'm now about to. Okay, and this is on the negative side. Okay, so each cis loop has the positive, each cis-loop ligand-gated ion channel subunit's extracellular domain has a positive side and a negative side, and both sides are going to contribute to binding sites. The positive side will contribute to a binding site with this adjacent subunit, and the negative side will contribute to a binding site with this adjacent subunit. Okay, so if we're imagining we're drawing out this cis-loop ligand-gated ion channel subunit here, these loops on the positive side here on this outer sheet are going to be contributing to this binding site, but the loops on this negative side, this inner sheet, are going to be contributing to this binding site, and here's one of these loops basically. Okay, and this loop is called loop E. Okay, so loop E is between beta 5 and beta 6 basically. Okay, now we're about to see the cis loop now, because this polypeptide is now going to cross back over onto the outer sheet over here, which I'll show like so. So here it comes. I'll try and go round the label there. Okay, and here it comes, and it will then go up here and form another beta strand there. Okay, and that beta strand will then be beta 7. So I'll just colour in beta 7 here. So here is beta 7, our second beta strand of the outer sheet here. Okay, now that portion in between beta 6 and beta 7, although it doesn't look like it, this is actually that cis loop. Okay, and I acknowledge that it looks nothing like what we've previously shown it as, but again, remember that's because I have separated these two sheets out so that I can show them simply. In reality, they'd be much closer, and therefore this would be a nice loop dangling down basically, and it would have a disulfide bond holding it together at some point with those 13 amino acids in between. Okay, right, so in yellow there, that is the cis loop structure. Okay, after which all the cis-loop ligand-gated ion channels are named. And remember, in the mammalian cis-loop ligand-gated ion channels, extracellular domains, that will have 13 amino acids in between the two cysteine residues, which hold the cis-loop together. Okay, right. Then what's going to happen is the polypeptide is now going to go back to the inner sheet again. Okay, and I'll show this here. So here it now crosses back to the inner sheet, and then it will go down like so, okay, and form another little beta strand here, okay, or rather no, I'll show it as a, well, it is a small beta strand, okay. The portion that actually contributes to the beta sheet is reasonably small, but it continues on, basically the polypeptide will continue on like so, okay, and then at the bottom here, what you're going to have is another one of these important loops. Okay, so here is an important loop there on the negative aspect, and I've also missed out an important loop up here, which is on the positive aspect. So let me just catch up here. Right, so this important loop on the positive aspect here on the outer sheet, this is known as loop B. Okay, so we've now got loop A, loop B, and these are contributing to the binding site basically between adjacent subunits. Then over here we've got that small little beta 8 here, okay, and then after beta 8 the polypeptide continues on even though it's not really involved in the beta sheet structure, and then at the bottom down here you then have another one of these important loops on the negative side, and this is loop F. Okay, so I'll try and put its name in here. Okay, so that's loop F down there. Okay, now what's going to happen is the polypeptide is going to return to the outer sheet over here, and we're going to have two final beta strands here. So here it now returns to the positive side here. We have another beta strand going up, and then another beta strand going down, and then this is where the polypeptide joins on to the transmembrane domain. So now what you'll have below here is the M1 alpha helix. Okay, right, so let me just colour in these beta sheets firstly, once again in red, and that's now this outer sheet complete. It just consists of these 4 beta strands, okay, and these two, to give them their names, this one is beta 9 here, and this one then is beta 10. Okay, now to add on another one of these important loops, the loop between beta 9 and beta 10 is another one of these loops that participates in the binding site, okay, and this is called loop C. Now, we are missing one loop. We are missing loop D, okay? Well, loop D is not actually a loop at all. Loop D is actually part of one of these beta strands on the inner sheet here. Loop D is actually part of beta 2 there, so it's a misnomer. All the others are loops, but loop D isn't called a loop, but in fact it's just part of the beta 2 beta strand, okay, which contributes into the binding site. So these 3 loops, as they're called, contribute to the binding sites on the positive side and the negative side of the extracellular domain of this cis-loop ligand-gated ion channel. Okay, so loop A, B, and C contribute on the positive side of the extracellular domain. Loop D, E, and F contribute on the negative side of the extracellular domain. Okay, right. So we'll call it there for this video, and in the next video we'll discuss this structure further.